All right, so this is center of mass. Basically, introduction-wise, the center of mass of a system of particles is a point that moves as though all of the system's mass were concentrated there and all the external forces were applied there. Okay, so basically, you're just trying to think of, almost like we always do, all of the mass being concentrated at one single point in the object. So, like, that's why when we draw a force diagram, right, we would just draw it as a dot, right, no matter what it looks like, okay, because we're treating the center of mass as where everything's happening, okay? You can try these balancing tricks if you want. There's a little video. This is kind of fun. We did this in summer school, or summer camp. Okay, rotating objects can be a little bit complicated, right? But it's actually not, because if you follow the center of mass of the object, right, that force of gravity acts on it just like as if it were a point particle, even though the bat is spinning around it. Okay, so the center of mass is where the forces would act. Okay, so if you check out this simulation, you can kind of see a live version of it. Okay, center of mass is usually pretty easy to find if it's a homogeneous object that has a geometric center. That's where the center of mass would be, right? So like right in the middle. If there's an axis of symmetry, the center of mass will lie along it somewhere. And also important to note that it doesn't have to actually be on the object. It could be at a point in space, like a banana. Like if you had like a banana, right? The center of mass would be like out here somewhere, okay? It wouldn't be necessarily on the object. It doesn't have to be, okay? All right. When you want to calculate these things, basically all you do is you sum up, okay, the mass times the distance of each particle or each part of the thing, and then divide by the total mass. Okay, you can see that also here. Okay, and it looks kind of like a complicated equation, but it's not as complicated as it seems. Okay, if you have a system of particles that's sort of like multi-dimensional, right? You can have an X component, a Y component, and a Z component, okay, which sometimes they'll just write as R instead of X, Y, Z, and R would kind of be like the combination of all of those. Okay, so it's easier if you just kind of look at it in a problem, right? So, or like in this one, do you see here the center of mass? This would also be like the balance point, right? So if you can find the center of mass of something, that would be like the point where you'd have to hold it to balance it, okay? So like if you take a broom or a meter stick or something and you sort of slide your hands along it underneath it, your fingers will stop at the point where it balances, like from out to in. You'll be able to find the balance point or the center of mass that way, okay? All right, so here's an example. A metallic sphere of mass 1 kilogram and radius 5 centimeters is welded to the end of a thin rod, length of 50 centimeters, and mass of 0.5 kilograms as shown above. Okay, this rod with the sphere will balance horizontally on a knife edge placed at a distance x from the end if x is what? Okay, so basically this means find the center of mass, right? We want to see like where would I have to put like a little fulcrum for this thing to balance. Okay, and clearly it's going to be closer to the heavy side, right? It's not going to be right in the center because it's not symmetric, okay? All right, so all you have to do, all right, is figure this out. It wants to know the distance from end A, okay? So we have to see what we've got here. So basically we have this rod, okay, which would have its weight acted at its center, okay, which is 25 centimeters away. Right, because the whole thing is 50, okay, and then this sphere would act at its center, which would be 55 centimeters away, right, because the rod is 50, and it said the radius was 5, okay, so if you want to find the center of mass, right, I'm just doing like m1x1 plus m2x2 divided by their total mass, okay, so I would do, let's see, the mass of the rod was half a kilogram, okay, times 0.25, or you could just leave it in centimeters, really. Okay, the mass of the sphere was 1 kilogram times 0.55, okay, and then I would divide by the total mass of that whole system, which is 1.5, okay? Cranking all that out, I get 0.45 meters, okay, or 45 centimeters away from the end of the rod. Okay, and if the rod is 50 centimeters, right, so you can see it's going to happen like really close over here, which makes sense, right, because that's so heavy. All right, so see if you have anything in your house like a broom or something that's heavier on one end, you can kind of move your fingers and see how that works. Okay, all right.